So the next typical or common moisture measurement unit is parts per million by volume, represented by ppmv. And again, the V is for a volume basis, not a weight basis. If you're dealing with gases, you usually deal in a volume basis, and if you're dealing with liquids, or solids for that matter, then you usually deal in a weight basis. Okay, so parts per million is a ratio, and it's a ratio of water molecules to everything else in your system. So if you could count the molecules, you could determine the ppm measurement simply by counting how many water molecules, counting the total number of molecules, dividing the water molecules by the total molecules, and that's going to give you a ratio. And if you multiply by 1 million, that'll put it on the basis of a million. So it would be how many parts per million. Counting molecules is not an easy thing to do. So, per the ideal gas law, the simpler way of calculating parts per million would be to measure the water vapor pressure, which is the pressure the water molecules exert, and divide it by the total pressure, which is the pressure all the molecules exert, multiply it by a million, and that will give you parts per million. So there's many hygrometers out there that if they're reading a vapor pressure or a dew point measurement, and a customer or the user is looking for a ppm value, then some math has to be done. So the dew point is measured by the sensor. A total pressure must be measured typically by a pressure transducer. Those two values are brought into a microprocessor. The microprocessor does the math. First, it would have to convert the dew point to vapor pressure, maybe using the Goff-Grach equation. The total pressure comes in straight away from a pressure transducer or a pressure transmitter. So with those two values, you do the simple math, and that gives you the part per million value. Okay. Just in terms of how small is a part per million, I decided to use the units of time. 1 minute is about 1 part per million in 1.9 years. Okay, so it's a very small number, 1 minute in almost 2 years, just to give you a quantitative idea of what 1 part per million is. Okay, so let's go back to our example and talk about ppm rather than dew point. So we've got our cylinder with a plunger, and in scenario 1, it's at 1 atmosphere. And then we squeeze that plunger down and we increase the pressure to 2 atmospheres. Okay, so we're at the same starting point in terms of moisture. We're at the vapor pressure of 0.0966 millimeters of mercury. We already know that dew point was minus 40 C dew point. If you do the math of dividing 0.0966 millimeters of mercury by 760 millimeters of mercury, and you multiply by a million, that's going to give you 127 parts per million. Okay, so then we squeeze the plunger down and we increase the pressure to 2 atmospheres, which is 29.4 psi, or 1520 millimeters mercury. Okay. What does the ppm value do? Again, in broad terms, does it go up, go down, or stay the same? We know the dew point changed, right? Dew point went from minus 40, I think we said minus 33 on the previous slide. What does the ppm value do? So the common answer is, well, the ppm value would change itself. But think about that. The total pressure is going up by the same ratio that the water vapor pressure is going up. So that in that calculation of ppm of pW over pt, that ratio actually stays the same. So the ppm value stays the same at 127 ppm in this example. So take a step back for a second. 2 points really to make. One is, here's a situation where the dew point was changed, but the ppm value stays the same. Okay, so again, that's why it's very important. If you're talking about dew point, you know what pressure it's referring to, especially when you're trying to convert it to ppm. Okay, and then the other point I want to make is more of a mechanical analysis of this situation. You've got a closed system, right? And ppm is a ratio of molecules, water molecules to everything else. In a closed system, you haven't changed anything. You haven't added any molecules of any sort. You haven't added water molecules, you haven't added any other gas molecules. So the ratio can't change. So, you know, on a mechanical side or a physical side, it makes very good sense that the ppm value stays the same. And again, in this case, 127 ppm. Okay, another very common measurement unit is parts per billion. And again, by volume, because we're dealing with gases. So ppbv, again, for a volume basis. It's the same basic equation, it's just on a different basis. So it's the water vapor pressure divided by total pressure times a billion rather than a million. And that's how ppb is calculated from water vapor pressure or dew point, as we talked about before. The graphic on the left talks about how small a part per billion is. So basically, 1 part per billion is 1 minute in 19 centuries. Not 19 years, but 19 centuries. So you can see part per billion is a very, very small number. Okay. Occasionally, somebody might want to know parts per million by weight, or ppmw, in a gas. It's not very common at all. However, when it comes up, there is a formula, again, based on the ideal gas law, that says ppmw is equal to the ppmv value times the ratio of molecular weights, and that ratio was the molecular weight of water divided by the molecular weight of the carrying gas. Those two values, have to be known. Obviously, the molecular weight of water is 18, so you'd have to know the molecular weight of the carrying gas to do the calculation of ppm by weight.